Great. So good morning or good afternoon, depending on whether you're on the West Coast in Europe or elsewhere in the world. And welcome to our 6th AskTOM office hours session for Spatial and Graph, our last one before the holiday season. And today we have a great focus topic. It's when graphs meet machine learning. My name is Gina Im. If you've been on prior sessions, you know that I'm a product manager for Oracle Spatial and Graph products. And today, we have our expert Sungpack Hong, our colleague from Oracle Labs. Sungpack is a research director. He came to Oracle after his PhD from Stanford University. And at the labs, he leads several research projects regarding graph data processing, large-scale data analytics, domain-specific language and machine learning, and he's just been instrumental in the development of the graph analytical technologies that are in the product today. So great to have Sungpack on board with his deep expertise in the graph area. And also not listed as a speaker for today, but online, in case you have any questions, is Albert Godfriend, our Spatial and Graph Solutions architect from France, who is seen in many locations working with many customers and partners all over Europe. So good afternoon, Albert, and to the audience. Before we dive in, a few of the usual housekeeping notes to keep in mind. All the participants' lines are muted, but please feel free to use the chat to ask any questions that come up. Our goal in office hours is to answer your questions and help with your development ideas. Don't be shy about that. We'll monitor that chat during the session, and we'll try our best to address all your questions. Do remember, however, we can't discuss any service requests or bug reports or licensing issues during the session. And you are free to post code into the chat, but just be reminded that the chat is visible to all the other participants on the line. Next slide, Sungpack.
1 second.
Thanks. So, as mentioned, today's is the 6th in our series of Property Graph office hours. We're targeting delivering to you topics for developers to quickly get started using graphs in your applications and to better understand how you can use graphs to add value to your business applications. Our previous sessions are all recorded and available, so feel free to visit our landing page at the URL listed to revisit any of those recordings that you may have missed or want to watch again. And in our prior sessions, we've shown step-by-step how to get going with using property graphs, how to model graphs from relational data, how to perform analytics, to visualize them and to query them. And now today, now that we have all that functionality under our belt, we wanted to dive deeper into compelling use cases that you may have thought of or you may not have thought of. And so we have Sungpack on board to share graph use cases, and in particular, how machine learning and graph can enhance one another to address specific use cases. Next slide. And just a little bit of context before Sungpack takes it away, the story so far. Next slide. As a reminder, Oracle does have 2 shipping products, software products that do support graphs. The Big Data Spatial and Graph product is designed to support graph data that's managed in a big data platform, whether it be Hadoop, HBase, or NoSQL. And it's supported both for BDA and commodity hardware products. It's licensable separately, and you can deploy both on-prem or on the cloud. For users that want to manage their graphs and analyze them using a database platform, Oracle Spatial and Graph also includes native property graph support, many different features and choices as well. You can deploy both on-prem and on the cloud, and our past sessions do dive deeper into some of the basic functionality that is included. Next slide. And as well, a reminder or a very, very quick intro to what the architecture of our property graph looks like. At the bottom, we offer the choice of storage and management of your graph data in either an RDBMS backend or HBase or NoSQL backends as well. We provide a graph storage management layer with a choice of access mechanisms. This is a Java layer that allows application developers to easily query, fetch, or filter graph data from the database through Java or JDBC or SQL. And on top, we provide for graph analytics a powerful parallel in-memory graph analytics engine. On the side, we have many different interfaces for developers to access this rich set of functionality, Java, Groovy, Python, as well as an expressive, easy-to-use graph query language called PGQL, and REST services, web service APIs, and notebook interface wrappers. Next slide. So graphs are very powerful because of the kinds of business insight that they provide, including things like an influencer identification, identifying fraudulent patterns, and generating recommendations. And today, we'll have Sungpack dive more deeply into this topic. So handing over to you, Sungpack.
Okay, thank you very much. Thank you for introduction. All right, let me start my session today. So when graph meets machine learning use cases. Right, let's go back to these benefits. Why do you want to use graph from the beginning as a data model, as opposed to just using relational data model as table? Right? I mean, there are a lot of many benefits that we typically talk about, and then some of these benefits has been discussed in previous sessions of this office hour. So that includes data model becomes more intuitive because like how the things are connected, you can just add the new vertices and new edges, and then just expand your data model as you go. And then additionally with PGQL and then clever implementation of it, then you can learn fast query over multi-app relationships in a very easy to use manner. And then because it's a graph, there are some tools that help you to visualize your data and then do interactive exploration on your data set. But in addition to that, for today's talk, we will talk mostly about this how to enhance your data analysis by using signals from the graph. What do I mean by it? So why do you, I just talked about graph signal. What do I mean it? Because, so when we are starting from relational data set and turning that into graph, what exactly are you doing? So by creating graph and by creating these edges, essentially you are capturing those fine-grained relationship between each of these data entities. And then because each of these vertices are the entities in your data set, whenever there's a relationship that you define, it can be like a foreign key, it can be a join condition, it can be something else, but whatever relationship that you define that you want to capture, you create an edge and connect those entities together. And then if you think about it in that way, now this graph model has more materialized information than the original data set. So if we can use this information, we may get more information, more insight, more useful information about the original data set. So that's the main idea, a fundamental idea behind using the graph for your data analysis. So the question is, exactly how? How can I do this? So in today's talk, I'm going to talk about basically 3 methodology in here. And then the first one is the most classical methodology, that is using graph algorithms on your data set. And this has been, okay, let's start with this. So this is when I say classical, it has been very long. It is well established, and then it's very useful to many of these use cases. And then the idea is that since you now have this graph representation of your data, and then we will rely on the power of the graph theory. because like the like graph theory has been like developed for hundreds of years, and then all these smart people has like defined what information, if given a graph, what kind of information you can get out of this graph representation, and then this like knowledge has been summarized as graph algorithm. For example, in this graph set, what is the most important like vertex in this data set, where the informations like always go through it? Well, what is most like popular or influential like vertexes in this graph representation, and then you can apply centrality algorithm to compute and then to find out those vertices. How one entity is like related to the other entity over multiple halves. You can compute reachability algorithm. What data sets are close to each other and then tie to each other and then create like some kind of community structures. You can apply communication algorithm to find out this information. In other words, this algorithm compute a very specific characteristic of your graph data model, and then you can use this algorithm result to get answer for your question. For example, like given a customer in my data set, what is the other customer that is close to this customer based on these graph relations? So let me go start with an example. This is an example that he showed like in Oracle Optional 2 months ago. So in this example, what we are going to do is we want to detect anomaly or anomalous cases in a public data set in Medicare data. So you can download this data from CMS, Center for Medicare and Medical Services, and then we are using the billing data for CY 2012. And in this data set, there are this is a transaction between about 900,000 like transaction between medical providers and CMS, and then with total amount of $77 billion for this year. So how does data look like? So basically, the data set looks like all these like medical providers or doctors, and whatever they do, this operation, prescription, treatment, and then whatever they do, and then for each of their procedure that they perform, they charge it to CMS. So that's like and then in other words, what doctors are doing what. So that's the that data set we are looking at. Next question. So in this data set, what kind of anomaly are we trying to detect? So we start from this observation. So doctors of the same specialty typically do similar things. If you are an eye doctor, you do eye doctor thing. If you are like a foot doctor, you do foot doctor thing. But what if there's a doctor who doesn't do his thing, but do somebody else's thing? For example, like your heart doctor doing plastic surgery. That is it is not normal. It is like it's an outlier in this data set. Okay, so that can he how if first of all, is there any cases in the data set at all? If there are some cases, how do you want to find such cases in a very like automated way? And then in this example, I'm gonna use how can you apply graph algorithm to find this kind of anomalies. So what you're trying to do here, we first start represent the CMS dataset as a graph. In fact, a bipipe graph that is undirected. So what do I mean? What do we mean by it? So we have these like medical providers or doctors, and then services they do. For example, Dr. Frankenstein, who is an optometrist, and then there are some services like prescribing aspirin. Once we have this data set, what do I want to do it is essentially like the approach is kind of like intuitive or simple. So pick a specialty like optometrist, and then starting you want to find out the distance defined by the graph, or which is sometimes we call a random walk distance. Given this this set of like starting vertices the eye doctors, and then find out other doctors that are close to this group, and then if there is any specific doctor that is close to optometrists, like in an exceptional way, And then how this distance is defined? If this guy is do a lot of things that these eye doctors do in common, then the algorithm, which is a random walk distance computed by PageRank, personalized PageRank, it becomes higher. Then it means that this person is close to these guys, even though he's not an eye doctor. And then can you apply? And then can you find out? And then it's simple. You pick these guys, starting from these guys, and then compute personalized page length on all the doctors in the graph. If there's any person that has high PPI value, exceptionally, we'll find him as an anomalous case. So the idea was very simple, and then we try to apply this ourselves. And then when we actually try to do this, we have to deal with a lot of practical issues. And then in this specific case, the issue was false positive. And in our first a naive application of this method, then we got a lot of false positive. Why? Because there are some popular common procedures. Like for example, initial patient visit, subsequent patient visit, like emergency department visit. These kind of things is typically done by every doctor in the data set. So, and then if this is what eye doctor does, this is what every doctor does, and then Dr. Y can be seen as close to Dr. X because of he's doing all these common things. So, how do we deal with it? I'm skipping all the details in this talk, but what we did was we first identified these procedures by learning some other algorithm. Basically, instead of learning PageRank, personalized PageRank, we can learn PageRank, which is the starting from every vertex and do random walking. Then by definition of this algorithm, things that every doctor does gets higher value, and then we can easily identify these kind of procedures. And then we treated them separately. And and then there are another source of false positive, which comes from closed specialties by nature. And then when you first looked at, after we deal with that, and when you looked at the data set again, there are a large group of doctors that are close to eye doctors. And then these doctors are called ophthalmologists, which means eyeball doctors. And then it was my first time to see it, such a job exists at all. And then just from the definition of the thing, you can easily say that they are doing the almost same thing as eye doctors. So, and then okay, that's interesting. And then how do we deal with it? So again, skipping all the details here. So I mean, if we just plot these values or PPR values from these two different groups, you can see a lot of overlapping between them. So we can apply some statistical technique, identify if there's any other specialties that has large overlap of the another specialty, then we just declare it as closed, and then we also treat them separately. So that was two the practical thing that we did. And then once we do this, do we actually see can you actually detect the anomalies? Yes, we did. So for example, this is one example of the anomalous cases in the data set. This specific doctor was a gastroenterologist, which means stomach doctor. And then we have a list of description of the procedure that this person provided. And then that looks like this: removal of eye fluid, preventive retinal detachment, removal of membrane from the retina. And then I omitted because I don't have space here. We have 30 or 50 of things that do. It all looks like related to eyes. So that's it. This is what we want to find. So a stomach doctor doing eye doctor thing and charging them to CMS. So I'm not saying this is illegal. I'm not saying this person is a bad person. I'm just saying that this is not what we, this is an anomaly. This is something outlying the normal distribution of your data set. And then we identified quite easily by applying graph algorithm. That was one use case. So Just like this instance, just like this example, we have very many other examples where we used applied graph algorithms to find interesting information about the data set. I'm not going too much details about it. This is another talk that we did in Open World 2017. So what we did was we given like a social network, Twitter network, we represent it as a graph. We apply some graph algorithm, and then we were able to find out like a bot or like a machinery account that generates messages or lead to it, some other thing, so that to make other accounts popular than others. So because they have different like communication behavior. So and then it was another successful project example that we showed. So what is the summary up to this point? Well, like the classical approach, classical application of the algorithm, what it is. So you have this graph, you have your data set, and then we create a graph out of this data set. And then we applied graph algorithm to answer very specific question. Like, and then this algorithm was deterministic, and then you don't need like any kind of like a pre-training before. It is you don't have any cold distance program at all. It just computes thing that you want to find and then give the result. And then it was very effective for many problems and application right now. Up to this point, we have like some examples of anomaly detection, influence identification, customer segmentation, topic analysis, and etc. And then all of these algorithmic based like approaches has been implemented in our in PGX, and then it is packaged in algorithm API, and then we are delivering this to many of our customers, and they are happy with it. And then again, and then another thing that I didn't mention here is like explainability, because you know what this algorithm is doing. Whatever the algorithm is finding, you can explain how and why I'm finding this result. And as you see in my previous use cases of like CMS, like data set detection, I know what I was computing. When I see this like event, like if it's false positive cases, I know why I'm getting this like false positive, and I can do actions to cut it out and then apply an algorithm again to find out the actual thing that I want to find. So that are the like usefulness of these algorithm-based approaches, and they are still very effective. And then most of cases, when people come to us, I just ask them to apply this technique. Okay, so far so good. It works very well. But then what's the issue? Why I'm having this session again? So the one issue that I have is you have to know what is this algorithm is, and then what algorithm should I apply to answer my question. That requires some kind of like training or some kind of like education on the developer side. So you have to be very keen on that. And the other thing is the trend. So these days, machine learning becomes a very big trend in IT industry. And then because of that, all the things now goes under, like all these data analytics goes under the name of machine learning. And then because of that, there are a lot of like existing techniques and tools that with in machine learning pipelines. And then you want to make use of it. Oh, I have this great tool that does k-means. I have this great tool that does this classification. How can I use my graph data and combine them into existing machine learning pipeline? That's what we want to do at this point. So, and then what's the problem here? So to repeat myself, what is the goal here? We want to apply machine learning techniques. Still, we want to make use of the graph signal, basically the interconnection between data entities that you materialize as edges. I want to capture them. I want to feed them into machine learning model so that this model can make use of this information. But there are some issues. But the one issue, the biggest issue that we want to address here is that this machine learning model, how do you want to to create a form of input that I can feed into machine learning model, while that's still and then this form should need to carry all the information in the graph, but still able to fit into machine learning. Why? And then this, because these machine learning models typically want to get some specific n-dimensional vector information, numeric vector. So they want to have some kind of encoding of your data that is represented as numbers, n-dimensional numbers. How can this be done? So I will talk about two different approaches. One is the first one is more intuitive and easy to apply. Basically, you want to generate features from by applying graph algorithms. So again, the idea is, in this case, idea is kind of simple. You have your original raw data, your original data set, which is tabular, and then you can easily encode it in, that can be easily encoded as a numeric values, and then fit this is typical machine learning pipeline. But since you have now this graph data set that captures this relationship, and then you want to generate additional features that can be combined with original features if you want, so that you can enhance, you can expand your machine learning model. Then how do I want to generate these features? This approach is simple. You just apply a bunch of graph algorithms that compute some numbers, and then use those numbers as a features. The rationale here is that because each of these graph algorithms computes something that captures some characteristics of this graph instance. So if we applied a lot of different graph algorithms, it might generate more features by using these features in addition to original features. You may able to get the information that is in the graph data structure. So let me just talk with one example. So this example comes from security application. So because obviously security is becoming more and more important topic with essentially for cloud business, because everybody wants to wants their cloud more secure than the others. And then as a side story, there are already a lot of interesting stories about using graph to enhance their security. Not only from our company, from other big company like Cisco, Microsoft, and Amazon, they have these kind of security graph stories already. Why? Because there are, in security, it is important to capture and combine different signals together. Because something happened here, something happened here, something happened here, it only becomes a real threat if these are correlated to each other. So in this specific talk, I'm going to talk about one specific instance of this security problem, which is malware detection from the network. So the goal here is that given traces or network packet captures, and then we will train a data machine learning model. You have one set of traces that come from activities from malware. Versus you have another set of traces from benign, normal web browsing kind of activities. Can I apply machine learning model to learn the difference between these two, and then so that whenever so that I can put this thing online, and whenever I see some packet trace patterns, it can detect and then say that, oh, it seems like there is some malware activities in your network. That's the goal. And then here we are applying a graph-based approach here, as proposed by some paper in 2010. So what was the observation from these guys? And then the idea was that, so I don't want to analyze each of these packets, because I don't see as packet body. They look all benign if I just look at one packet. So instead, they want to collect up these traces as a graph. And then then the thing that they talk about in this paper was that the graph that is created by these malware activities have different patterns than normal activities. like in this specific example, when you go there, if there's a malware in there, that it has to download something, and then you start to generate like post downloading activities to a bunch of different like target sites, and then that becomes a like different like shape of this activity graph. So what they want to do was, okay, can he characterize this kind of like graph and then differentiate it to benign? So in this approach, have I talked about it? And then they apply this technique. So how do you want to like characterize this kind of graph? And then what they proposed in the paper was that, okay, let's was this algorithm based like approach. Let's compute some graph algorithms on this graph and extract some numbers, and then use these numbers as a signal to characterize this graph. Then what we did in the lab was we just tried to implement this algorithm, these approaches, as on top of PGX, which is the part of big data separation graph. And then we generate all the features as proposed in the paper: node site, edge site, average degree, eigenvectors, page length, clustering coefficient, all this, and then these algorithms are all in the PGX packages. And then we use PGX to generate these features, and then you applied machine learning techniques such as TensorFlow to train the machine learning model based on these features. And then what data set did you use? We used two data set. One data set from like malware packet captures from this site, and 1,000 benign captures from the other site. Okay, and then actually I have we have a notebook demo that we when we did this experiment. Basically, this is a notebook based on like Zeppelin. So, and then as you can see that we have this PGX paragraph. Basically, we load one set of graph, and this one was the other set of graph from benign packets. And then this shows that for each graph ID, like what is the size, number of vertices, and number of edges in each of these packets, packet traces represented as a graph. As you can see, so there are some like large like trace instance that has like 3,000 like vertices, or and like 1,000 vertices, and then there are some like edges numbers also vary from like 19,000 edges to like 100 edges here as well. So just by looking at the size of the graph does not tell you is it benign or malicious. So what he did from this data set, for each of these this graph or set of graph, what he did was that we write some procedure for each of these this graph. You want to apply this algorithm, analyze that degree centrality, analyze the local clustering coefficient, analyze that in degree, page rank, eigenvector. We compute these algorithms, and then we get the values, and then essentially we just print it out as CSV file. And then one from like malware, one from benign, and then we just like export this CSV file, and then this is one part of the work. And then once these like features are generated, we use some other tool, and then to train machine learning, apply machine learning technique like decision trees or neural net to classify these different traces. Then I'm going to skip all these details. Basically, we use TensorFlow and sklearn and using Python API. And then when it did train the decision tree methodology from this data set, and then we shuffled up like test the training set and tested. I think it was 8 to 2. And then we apply this decision tree and then to validate the result. And what was the result? The result was like for this data set, it was like 100% accuracy. There was no first positive, there's no first negative, and then it just like get 100% accuracy on this by just when you train on these features. Similarly, we also try to apply different like a classifier using convolutional neural network. And then the result was almost same. So in the end, you get very high after some iteration of training with some parameter tuning, at the end you end up with a very high accuracy. So that was what he did with this this technique, applying. So to go back to repeat what I just said, to summarize what I just did. So what we did. So you have this graph data set. You want to feed that into machine learning model, such as TensorFlow, like CNN, or TensorFlow, or like a decision tree. In order to do that, you need a representation that captures the information from the graph. And in this specific methodology, what do? We apply graph algorithms to compute some numbers. And for each of these graph instance, compute some numbers and use it as a feature that can train on this on this model. And then that actually is in this example, it works very well. And then by those information were good enough to distinguish one set of the network pattern, which is malware activities, as against the other set of activities. Okay, that looks great. So this is like things that you can do right now, because from the demo that I just showed, I just used the public PGX API to load the graph and do PGQL and then to compute something, and then just simply printed it out as a CSV. So this is all on the public our current released features, and the feature you can always reproduce these two demos with what you already have now. So from now on, this is you are seeing this safe harbor statement once again, because I'm talking about things that we are doing in the labs. So contents in this section discuss recent technology from like how do you want to combine graph and machine learning in a more systemic way. And some of these techniques are experimentally implemented in Oracle Labs, and therefore they are not part of Oracle Graph products yet. So that's my notice before I go into next slide. Okay, let me go. So what I just talked about, applying graph algorithm as is. That's one. That was first section. Second section, apply graph algorithm to generate new number features and feed it into machine learning model. That was the second section. So there are still issues. So why? Because I mean, if you remember what I just talked about, this like security thing. So we picked up that seemingly arbitrary set of algorithm to characterize the graph and feed them into machine learning model. Where did it come from? How this like original author of this paper pick up those algorithms? Is it sufficient? Are these numbers like also on each other? And then if I have another like application, would it still work for the application with this specific set of algorithm? What more should I compute? So that's the questions that you will have. So in other words, we need a more systematic like approaches, systematic methodology that turns graph information into n-dimensional numeric representation or embedding, so that it can be fed into the machine learning model while you want to keep the information in the graph as much as possible in the other representation. And then for the remaining 15 minutes, I'm going to talk about two embedding techniques. One is called vertex embedding. The other one is called graph-led embedding. Let's go with vertex embedding first. So here, what is the idea here? So I'm just continuously repeating myself. You have this You have a graph representation, and then you need a numeric representation of this data set to feed into machine learning model. What are the information that you, if I'm translating this into transforming this into the other one, what are the things that you want to keep? In this specific case, I want to keep the distance between entities in this data set, and then the distance is defined by the graph. In other words, if I have two entities, x and y, in this graph data set, if they are close in the graph, by some graph distance metrics, such as random walk distance that we talked about in the first section of the talk. If when I turn these entities, and each of these entities become a numeric n-dimensional vector in this representation, if we compute the distance of these two vectors, like inner product, then they should be close enough. So if they are close in here, they are close in the vector space as well. That's the thing that we want to achieve when you're turning this into the other. And then once you have that, then if you train the machine learning model based on this representation, and this model will see that keep the information what entities are close to each other. That's what this vertex embedding is trying to do. Exactly how do you want to do this? I need to go really quick and then just glide over it, because if you go too deep, it requires some background and and information. So it doesn't have, we don't have too much time to do it. But I mean, the idea is not that complicated, because I mean, what I need to say is this is not just us. Like, there are many people who is interested in this problem, and there are a lot of different techniques to how to do this. And then I'm just introducing one specific topic that is like kind of one of the oldest one that Frontier pioneered this problem in KDD14. And then they apply some machinery or techniques from that is from modern natural language processing. Then in there, there's a technique called word-to-vec, which like from like a lot of like sentences, like sentences, they want to learn the distance between words in the vocabulary. For example, the word king and queen should be close to each other because they often appear together in sentence, as opposed to the word king and maybe capitalism is far away, because you rarely see those two words in the same statement, same sentence. So they have this technique called word-to-vec. If you feed a lot of like sentences in this machine, then it will learn the distance between these words. And then the technique of behind this like the works is that given a graph, we will treat each of these vertex as word, and then they will just simulate like a graph distance by performing a lot of random walk, and each random walk traces become a sentence, and then they feed that into this machinery so that they can learn the distance between the words. And then because here we prefix the words, they can use now this machinery will learn the distance between vertices. So that's where that's the approaches. So let me just give a quick example. So we apply this technique to like some artificial program. So we have a real data set from university where the students are like taking some courses. Okay, and then we just make it more interesting by only some of these students are labeled from of their majors or department. Okay. And then by looking at this information, what students go to what classes together with some of these labeled students, can you predict the label or the department of the other student? So why I will looking at this problem? It seems very artificial, but you can still consider this as a mock-up problem of customer segmentation. So if you just replace student into customer, courses to what are the items or services they purchased, then you are trying to predict the label of new customers by looking at what they purchased. Right. So yes, I'm skipping all the details here. So essentially what he did was that, okay, here's the first, like instead of looking at this like relationship at all, you just use table view. I have these students like age, students like gender, students like dormitory, and they have some information about the student. If you create the machine learning model, just only look at this thing and then try to predict the department, you don't get very far. Okay, And then what is this blue bar? Blue bar is applying algorithm directly on top of it. Given a student, like you look at this personalized page length, like lambda walk distance on the graph, and then try to use this lambda walk distance, and then estimate its department. And this is how much you can get by applying this algorithm. Right. Then what he did was, okay, starting from this graph, we extract the distance information using this debug technique, and then make a classifier model as after using these features, and then we train them, and then that was what this green means. So what do I mean? What this plot shows that, because if you that means that the green thing is almost as close as blue, which is the algorithm, means that it seems like this debug is preserving the information that you can get from the graph. So you will get almost as good number as applying the algorithm directly on the graph. So, but it's still lower than, it's still substance, like I already lost some information by translation. So why do you want to do this? Because once you have these features now, because these features come from this like relationship, you can combine this information to other sources of information, such as their dormitory, such as their age, such as their gender. And then now you have more information than just looking at one side of it, because it's all like it's in a form that is easy to manipulate. You just combine them together, and then make your model richer, and then train on it, and then you get more you get improved your seeing by this much. So that's why we want this kind of technique. So for right. So that was like part one of my story, and then part two of this embedding is graph-led embedding. So in this vertex embedding technique, what you're trying to like encode was the characteristic of each vertexes. Okay, and then we want to keep the distance information between those things. And now we are looking at slightly different problem, because we want to capture the similarity or closeness between the shape of the graph or each small graph instances. So here's some artificial problem here. So this is a graph representation of the characters in like classic literatures. So Odyssey, Beowulf, Romeo and Juliet, and Hamlet. Okay, and if you see that the shape of this graph in this very old literature, like Beowulf and Odyssey, are different from some from what comes from Shakespeare, because here you have only one person in the middle, the main character, and all the other characters are like reacting around this main person. But now with this Shakespeare, the plot becomes more interesting. You have like a lot of like interaction between different cast of characters to each other, and then so now you can see. I mean, if you think about it, you can actually see the differences. So my question is there any way to systemic way to extract this difference between this small graph, and then tell, okay, given this new like shape of graph, this plot characters, this relationship looks more like this or more like that? Is there any like a systemic way of doing that? So that's the problem of like graph-led embedding, graph embedding. So given a graph, I want to extract a feature or number of like a vector that represent the shape or the property of this specific graph instance, so that we can compare different graphs if they are similar to each other or not. I'll skip I'll skip some details here. How do you want to do this? Again, we are using some machinery from like modern NLP techniques, but in this case we enhanced what was proposed in the paper a bit by adding our own some extensions, and then you should do this instead of using vertices. You should use edges. You should use some properties, and then we do something about it, and we extended it. And then we have one more example here. So in this example, what you are doing is looking at some like biochemistry information, like molecules, and these molecule data came from some public domain data set. And what you are trying to do is, given a molecule, all right, maybe I should just do this. Given a data set, can we classify if this comes from cancerous data set, or it's not cancerous, or this is like a binary classification, or is it like two type of protein, and then is this given a molecule represented as a graph, does it look like the protein type number 1 or protein number 2? So that was the classification problem that we were solving. And then the green one was what was proposed in the paper, and the red one is after we apply our own in like enhancement. And then as you can see that we can easily like identify, we improve like the accuracy quite a lot by using our own techniques. Okay, I'm gonna so I mean this, and is there any like more business oriented questions or a problem that I can apply this problem? And then this is the second example. So we are working with like some people in like financial crime domain, and then they are solving the problem of anti-money laundering. And in this problem, this is more serious. And then what they do, I mean, I need to skip all these things, but they have this like monitoring the transaction between the account every day. And then they, at the online step, they just, for every transaction that happens, they just flag it out. Flag. And then once a day, once like a couple of hours, once a week, they apply this algorithmic approach. They like, for each of these events that happen, they correlate them together if they are close enough. And they create this, what they call a case. And then this case is composed of the account and business entities, and what are the alert flags that you attach to it. And then each of these cases looks different. And then what they are doing right now, as of today, is that given a case, they just compute some values, some algorithm manner, and then it goes to human investigator, make a decision. Oh, this case looks serious. We need the official like investigation, so it becomes larger. It looks okay, it can happen. I'm going to close the case. I don't know what happened. Let's wait a few more days so that if we can have like something more happening around this case. So these cases happen a lot of times, and then for each of these cases, a person should work on it. So question is this graph ML technique can help making decisions here. And then we have some example, like given a case from my like database, given a case to happen right now, has there been any cases that look like this in history? Then what we did was like we trained this shape of the graph using this technique, and then to quickly retrieve what are the most likely things that happen in the database. That's task number 1. And task number 2 is that, okay, that's like, if you can do this, why not just giving the answers directly? Okay, this looks like very like something that happened in the future, in the past, very serious. I recommend you to official investigation. So can the machine give this recommendation based on the history? So that's the things that are ongoing. We don't have a good answer yet, but this is one application. Right. I need to wrap up my talk. So okay, so this graph machine learning thing is not just us. It's not just some random people. Many people are interested in this problem. And not only those two techniques that I talked in today, there are multiple different techniques discussed, developed, and then evaluated. And then it's not just some random person, like even in other industry, like Alibaba, Google, Pinterest, and they are looking at this problem and then applying it to solve some real world problem at this point. And then we are following that. We are trying to improve it, and then we are working on it in Oracle Labs. So yes, we are trying to improve the scalability of this methodology. We want combining structures and then role observation in a systemic way. We want to make it easier to use, etc. There are many issues. So in summary, so what I have talked today. So you can use graph signal, a relationship between data entities, to enhance your data analysis. Why? Because you are now using this information, this relationship information directly to solve your problem. And how you can do this, I talked about three methodologies. The first one is applying graph algorithm. If you know what you are doing, this is a best way to do, because you don't need training. It is explainable, and then you don't there is no like a cold start problem, and then it gives direct answers. So it is currently like fully supported. And then there are, and then I talked about combining this graph information to machine learning, like modern machine learning pipelines. Then I talked about the easiest way of doing it, which is just compute some algorithm to extract out some information and then feed it into machine learning. And then in the last section, I talked about this embedding technique, which is a more systematic way of turning graph information into vector space so that you can feed it into modern machine learning tool. And then in general, graph analysis has many applications, specifically like domains like security or anomaly detection or like collaborative recommendation. Why? Because this information, so information they are looking for resides in this relationship. It's not, if you just look at each cases individually and then try to learn something out of it, it takes forever. What you need to do is you have to like grab this relationship or lack of relationship, and then use this information to answer your question. Yeah, and then graph is a great tool for doing that, because it captures this fine-grained relationship and materialize it as edges. I think that's it.
Great. Thanks so much, Sungpack. A great look at all of the shipping and technologies under development in this very interesting space and a wide range of use cases. So thanks a lot. I'll quickly share some resources with the audience for more information. Next slide, please. So if you want to learn, read more, look at technical information, or a wealth of further presentations delivered both by Sungpack and other folks on our Graph Technologies team at Open World this year, here's some great URLs for resources to take a look at here. We'll also be posting these slides up on the AskTOM site after the session. Next slide. We're also heavily on social media. Feel free to follow us and join our groups. Next slide. Finally, wanted to highlight we have an analytics data and data summit coming up in March of 2019. This is the premier event for Oracle technologies around the data of analytics and data, and we always have a wealth of offerings from the spatial and graph technologies side with our own dedicated track over 3 days. Our call for speakers is now open. We encourage folks with interest in technology applications and customer use cases to consider presenting. The deadline is January 27th. Visit analyticsanddatasummit.org for information, or feel free to ping me with more questions. So with that, we have a few minutes left for questions. Actually, sorry, one more slide, please, Sungpack, thanks. I'll just display, again, the AskTOM landing page for recordings and information about the series. So, Sungpack, we did have one question during the session from Melly, and she asked about the architecture used for the second use case on security that you shared. Could you comment on that? She's interested in the size of the PGX server, memory used, etc.
Yeah, I mean, I think this was this thing. I mean, this data set was quite like small per se, because I have like a few thousand graph, and each of these thing is has almost 10,000 vertices and edges. So even if combining everything into one thing, with very small amount of memory, less than 10 gigabyte, I think, you can easily work on this. And then this algorithm computation is taking very a little time for each of these small graphs. You just execute it and then just compute these algorithms, and it was very fast to do it. And then what happened after this PGX is done, we export it out as a CSV, and then we use some Python library. I think we use TensorFlow to do the second part of the training. And then, as you know, that actually the second part takes more time than first part. because it's machine learning and training thing. And then I think the person who actually did this hide it out, but I'm pretty sure he did a lot of like parameter tunings so that he can get better results.
Excellent, and that's pretty impressive in terms of the performance that was accomplished as well as the level of analytics. So last call for any questions. Feel free to enter them in the chat if you have one. You have about a minute left. Okay, there's one more from Melly. So she's asking how much of the machine learning capabilities that in the use cases you've shown are in the products, and how much is in research today in the field in general?
Yeah, I mean, if I go back to like my three, it's like I have these three sections, right? And then the thing that I talked about in the first two sections is I'm just using all the things that is already like public. So these two demos, you can reproduce it with like current version of PGX. Like I can provide the script. I can share this notebook. I can share this R script that you use. You can replay it. The third one that with the embedding techniques is the one that is not public. We have some experimental implementation on top of PGX, and then it is not. It's still experimental. That's not public yet.
Great. Thanks so much, Sungpack. So we're just about at the hour. A lot of information and interesting use cases. I agree with Melly here. So I'd encourage folks, if you have questions or some potential use cases where you see applications of these technologies, feel free to contact us. My Twitter handle was posted, and you can also reach us through the AskTOM DevGym website, where there's a question form available there. We're always interested in talking with folks about your potential use cases and helping you out with understanding how you might be able to apply these at your organizations. So with that, we've reached the hour. Thanks to Sungpack very much for your time and expertise and sharing that with all of us today, and to everybody for joining us either in the afternoon or in the morning. Have a great rest of your day, and we'll see you on our next AskTOM session. Thanks a lot.
Thank you very much. Bye.